record the lectures because I know life happens. So you are being recorded. If you don't want to be recorded, then just when you put your hand up, say, switch the recording off, and I will. So what I was saying is learning is an emotional enterprise. Okay, you don't learn something that you don't particularly want to learn. And if you have to learn something that you don't particularly want to learn, it's an uncomfortable thing. But more generally than that, often in order to learn something, you need to acknowledge that there's something that you don't know. And that acknowledgement can often feel a little difficult. It's not great realizing, this is a thing I don't know. There's an emotion involved here. So, and particularly when you're learning at an intense rate, which is what will happen with this course, and you're learning quite complicated things, it can often start to feel quite anxiety-provoking. It can feel stressful, however it is that you respond to the not knowing. And I think it's a problem when people just kind of set that aside and pretend it doesn't matter, because it tends to build up. So instead, what I recommend that you do is you be kind to yourself and you're like, this is frustrating and I'm stressed. That's how I'm feeling. Do something to work with that and then get on and do the work. So acknowledge your feelings. But the other aspect of it, which I also don't think gets talked about, is the sheer joy when you get something that you've been struggling with and it's like, yes, I got this thing. So please, and I hope that there will be times when you get to do this in this course, when you have struggled with a topic and then you get it, celebrate, be joyful, feel that joy, because that's kind of why we're here. We're here for the joy of learning. And we're all human beings. We're all doing our best. Life happens. Let's just be kind to one another. I think we've had a couple of years of that really hitting home. For you, please, I know life happens. You might have the best plans in the world for what's going to happen in the next 6 weeks, and then something happens. If it does, tell me as soon as possible. Because we can make plans, we can sort stuff out. I can give you extensions, but only if I know. The hardest thing for me as a lecturer is when someone comes to me at the end of the 6th week of a course and says, so this thing happened to me in the first week, and I haven't done anything for the last 6 weeks. What can we do? And at that point, I have to say there's nothing. Okay, so please come to me. I am really generally very approachable. And we will do whatever we can. Okay, I want you to love multivariable calculus and pass this course and have a wonderful time. That is my reason for being here. Okay, phew, course manifesto. Okay, there's a whole schedule. Don't get too terrified. It's going to be fine. Format, as you know, 6 lectures, 90 minutes each, 1 every Monday, 2 tutorials each week, 90 minutes each. In the tutorials, it's really important that you be there, because that is where you will actually get to do the stuff. Okay, I tell you about stuff, but that's not very helpful. You need to do stuff. And that's happening in the tutorials. In terms of assessment and evaluation, again, you'll see that the emphasis here is really very much on you need to be just getting your hands dirty with this stuff, and so most of the assessment is geared to encouraging you to do that. So, apart from the inevitable midterm and final, which will be fairly standard, we have 2 kinds of assessment, and they will be pretty much every week except the midterm week, because that would be cool. So every week in the tutorial, on the Thursday tutorial, the last half hour, you will be given a quiz on that week's material. You do not have to do fantastically on the quiz. In fact, if you just write down, okay, I realize I need to go and learn this, this, and this on the quiz, that is fine. At the end of the quiz, you will upload to Canvas whatever you wrote on your quiz sheet. You will get a 0 if you just hand in a blank sheet. You will get a 1 if you wrote anything on the sheet that makes a valid attempt. So whether you tried to solve the problems, you explained what else you need, just something. Okay, all right. Then you will take your sheet, because you will have uploaded a copy. You will take your sheet home, and by whatever means necessary, other than asking me, so talk to your friends, use the internet, speak to your grandmother, whatever you need, solve the problems correctly and completely, and grade what you wrote in the quiz. So maybe you got it completely right during the tutorial, then you put a smiley face and a tick and you're done. But maybe there was some work that could be done. You write all that on that, and before the next tutorial, you upload that to Canvas. And you'll be graded a 0, 1, or 2, 0 if you did nothing, or if your corrections are completely wrong. A 1 if you did something, but maybe your corrections are not quite right. And you get a 2 if your corrections are completely correct, even if it's just putting a smiley face because you got everything right. Okay. Why am I doing this? 2 reasons. The first reason is you need to have a chance to practice in a kind of examish setting, just writing down maths, but it's not too high stakes, because I know some people, myself included, have kind of maths anxiety that kicks in. So it's just getting a chance to practice, getting your head around, I have to do maths right now in this, okay? So that's about that. And the second thing is, mostly in life, no one gives you a solution manual. Mostly in life, you don't have an instructor who grades what you did and says, here is where you made your mistakes. Mostly in life, you have to figure it out. So let's practice doing that. But the other good thing is, mostly in life, you also don't just sit in an exam room and then have to figure it out entirely by yourself. Mostly in life, you have people to help you figure it out. I would also recommend, although you don't have to, for these tutorial assessments, that you start making a note for yourself of the kind of mistakes that you make. So you might find after a couple of weeks that you realize, I'm always making stupid mistakes. I keep saying like 2 times 3 is 4, or just like stupid algebraic errors. Use that to change how you do problem solving. So for me, and you will see this throughout the course, I am just terrible at algebra, particularly when faced with standing in front of a lot of people. And the solution for me is I just have to slow down. I have to tell people about it and get other people to check. That's the kind of thing. You might find that the kinds of mistakes that you make are more conceptual, and that might be dependent on the quiz, in which case then you know that's what I need to go study. So please use these tutorial assessments, which are very low stakes, as a chance to really improve your own knowledge of your brain and figure out where you need to do work. Okay, so that's weekly tutorial assessments. We'll also have almost weekly quizzes, except not in the midterm week. And these are just, they're on Canvas, they're multiple choice, but they will require you to actually do some calculations. And they're just the kinds of things that you should be doing in your homework exercises. I just want to make sure that you do it. You have infinite attempts, and although there is a deadline for the Friday of each week, if you need an extension, you just email me, I give you an extension. No questions asked, because it takes us all different times to learn stuff. The only requirements that I have are that if you want to be eligible for a resit, by the time you write the final exam, you must have done all 5 weekly tutorial assignments and all 5 online quizzes. Okay? But extensions will be given up to and including that point. Okay, so you figure out your brain, you take as long as you need to learn this stuff, but be aware, we're covering a lot, so trying to keep up with the weekly schedule would be good. Okay? Midterm exam will be in week 4, it will be during the Thursday tutorials. Final exam will be in week 7, who knows when. Okay.
Should be on Monday. We have it in our schedule.
Okay.
On Tuesday, sorry, should be on Tuesday.
Okay. Currently on Tuesday, but who knows? Right? I've given up trying to predict what scheduling is going to do.
Yeah, no, it's in our schedule, so.
Yeah. Okay, but great. Okay, so there we know. Roughly week 7.
Week 7 on Tuesday.
Should be, probably, maybe.
Olza does not decide to change it.
Well, yes.
It's, you know.
You're so naive and trusting.
Yeah.
All right. Okay, so I think that's pretty much everything that you need. In terms of how we're going to... So online quizzes, 20%, tutorial submissions, 10, midterm 30, final exam 40%. 5.5 to pass the course. If you have done all your online quizzes and tutorial submissions, then if you don't get a 5.5, you're automatically eligible for a resit. Okay. Questions?
Yes, but if we miss one tutorial on Thursday, when we have to do the submission, how do we do it?
Good question. Okay, so if you missed the Thursday tutorial, then you get a copy of the quiz I'll put it on Canvas. You do it in your own time, without, like you would have in an exam, and I'm trusting you there. You upload that as your first submission, and then you correct it, like your second submission. And you just let your tutor know. So I mean, if you're ill on that Thursday, obviously don't write the quiz on that Thursday, that would be stupid. Just let your tutor know. And I've told the tutors extensions are automatically granted. Okay. You just have to do the work. I don't care when you do it, you just have to do the work. Yep.
Are exams floating and offline or online and book?
That's a good question. So my current thinking, but it's not final, is the exams will be closed book, offline, but I will give you a formula sheet, and you can bring in one A4 page of your own notes. But let's talk about it. I mean, I think that will be fine, and I think it will give you a good chance to have enough information as backup, but also test your abilities. But let's see how we go in a week or two. Yeah? Okay, good questions, more good questions. Okay, to the maths. All right, so what are we doing here? So I know that I have TKE people. Welcome. This is particularly a course, so it is multivariate calculus in general, but the goal of it is predominantly for MSP students who are wanting to go further in physics. Because in order to go further in physics, you're going to have to do electromagnetism, and these are 4 equations that you need to be able to work with in a deep and profound way, and single variable calculus will not get you that. So we need multivariate calculus. So I will keep it pretty general, but occasionally I will kind of point in the physics direction. I hope that's okay. And if you have any applications of this kind of beautiful stuff that you would like me to talk about, I would love to. Let me know. Okay. So the thing that I would say about this is we have 6 weeks and 6 90-minute lectures. In pretty much most other universities, this would be probably a 15-week course with about 45 lectures. So I have really slimmed it down to the bare essentials. I am putting stuff in the tutorials to give you the practice, but understand you're getting an overview. So if you want to go into kind of more multivariate stuff, for example, if you went into some data science, you would probably need to go deeper into some areas. Okay, but I'm going to give you what you need in order to solve Maxwell's equations when you get there. Okay, and hopefully enough kind of hooks that you can be like, oh, I realize I need to go and do more in that direction if I need to. Okay, so, phew, what are we doing today? We're going to talk a little bit about analytic geometry and vectors. Who has done linear algebra or seen vectors and cross products and things like that? Fan? Okay, anyone who hasn't? Okay, then we're going to go quite speedily through that, which is fantastic. And why we need the vectors? Well, because multivariate calculus deals with 3 dimensions, and suddenly you need to have vectors. But we're going to need them particularly when you talk about planes and lines, which are going to become kind of our basics for a lot of what we do. And then we're going to move on to talk about vector functions and curves and parameterizations. All right, so here we go. I'm actually going to, since you've mostly seen this, I'm going to talk through quickly. We are mostly going to work in your usual XYZ coordinate system. I might give you a tutorial talking about spherical and cylindrical coordinates, but generally speaking, we're thinking about our coordinate system looking something like this. And as you probably know, if you have a point in 3 space, so this x coordinate is coming out of the board at you, you can find the distance from the origin to that point by using the extended version of Pythagoras. Challenge for homework: if you take any 2 points, show that the distance between them is given by that in 3 dimensions. So this is just getting you moving from 2-dimensional thinking to 3-dimensional, but it's Pythagoras. Okay, So you've all talked about vectors, you know about this. Again, be very clear in your mind. A scalar, something that only takes one number to describe. A vector is some quantity that you need a direction and a magnitude. And one of the things that is going to become really quite important, and I think is a tricky thing that I didn't really get early on at university, vectors don't have a starting point. They're a magnitude and a direction, and you can start them wherever you want, wherever is convenient. So sometimes it's going to be useful to think of a vector as starting at the origin, but sometimes you're going to want to start it somewhere else. And in fact, that becomes very clear when you talk about adding vectors. If we've got two vectors, AB, so running from there to there, and BC, it makes sense to start vector BC, if you're adding AB and BC, shift your BC so that it starts where the first vector ends, because then you can see where your actual sum of vectors goes. But, as you probably know, if you were thinking about forces, then it would make more sense to draw your two vectors like that, starting at the same point. If you were trying to find out the resultant force, it makes more sense to start BC here, because then you can find a resultant force. So get comfortable in your mind with this fact that vectors don't have a starting point. You can move them around. Okay. So you know how to add vectors? Yes? Yes? Yes. Awesome. Okay. I'm not going to go through that then. Other useful things about vectors, we know that we can scalar multiply them. So this is the useful thing. They give us a direction, but once you've got the direction, you make it as long as it's useful for you. And in particular, we care about our three coordinate vector unit vectors. So we use I hat is the unit vector in the x direction, which is typically coming out of the board, j hat going that way, and k hat there. And these are the standard basis vectors. There they go. Okay, and this gives us a useful way of describing, so the notation that I will use in this course for vectors, which might be different from what you've used, I will either use, so vector r, which has components x, y, and z, using these square brackety things, or if I want to be very clear about which coordinate system I'm talking about, x units in the I hat, y units in the j hat, z units in the k hat. Interchangeable. Sometimes it makes sense to use one, sometimes it makes sense to use the other, and if you have notation that you're much more comfortable with, you're welcome to use that, so long as you can translate into this as necessary. Okay, and you know that adding vectors, I mean, I like the square bracket notation because it just makes addition super easy and you don't waste ink. So worthwhile to just have a glance through the properties of vectors when you're going through these notes. They behave, as far as addition goes, exactly like scalars. So they're commutative, multiply it by 0 and you get 0, multiply 1, you get the same thing back. Addition of vectors works like scalars, which is delightful. It's the multiplication that gets hairy. One of the things that you want to do, because your vector is something that has a direction and a magnitude, sometimes you want to find that magnitude. This is how you do it. You square the components and take the root. It's Pythagoras, really. And if you go up to n dimensions, you will just end up with squaring n things and then taking the root. So, yay. And this enables us to talk about unit vectors, which I don't think are in my notes, but you have the idea of a unit vector, which is the vector in the same direction as the original vector, but that just has length 1. And we would usually write a unit vector like this. So it's the original vector divided by the length of the vector. So that's going to be a useful thing to do. Sometimes you don't care about the magnitude, or you want to specifically just talk about the direction, find a unit vector. Okay, dot product. We've all seen the dot product. Good old dot product. So the dot product is usually traditionally taught, and when you calculate just the dot product, you will look at it like this. So it's vector A dotted with vector B, and you're just adding together corresponding components. So the thing to think about this is, it's called a scalar product as well as the dot product because the result is a scalar. And it's kind of an odd thing to do. Most things where you, for example, take two numbers and you add them together, you get another number. But now we've created an operation here where we take two vectors and it spits out a number. So it's a little bit of an odd thing. But it turns out to be quite useful. Very simple to calculate. You don't need to go through those. Mostly what it's used for is because it gives us a way of finding the angle between two vectors quite quickly. So you can go and prove for yourself that if you take A dot B, it's the same as taking the magnitudes of A and B and multiplying by the cosine of the angle between them. But pretty much what we do is reversing this and saying if we know those two vectors and we want to work out the angle between them, then we can rewrite that equation as cos theta is equal to dot product over magnitudes, and we can work out the angle between them. So usually that's what the dot product is for, and specifically it is super useful if you want to check if two vectors are orthogonal. Because two vectors are orthogonal if and only if their dot product is equal to 0. And as you'll see as we head along through this course, it's going to be very useful for us to have a quick way of checking whether two things are perpendicular or not. Okay, so just to say, I did put these notes up online, and once I finish the lecture, I will tidy up the kind of filled in version that I've got and put those up as well. So don't stress too much about getting all the notes down. Okay. So the other way that we can multiply vectors together is the cross product, also known as the vector product, because with the vector product you put in two vectors and you get out a vector. Okay. The thing that is slightly odd about the vector product or the cross product, unlike the dot product, which you can define in any number of dimensions that you choose, the cross product is only defined in 3 dimensions. Only 3. Not 2, not 4, just 3. There are kind of extensions of the idea of the cross product going to higher dimensions, but that's beyond the scope of this course. But to take what we use the cross product for and create something similar as you go higher. How do you find this bunny? You pick your favorite method. Everybody has learned their way. I still use the way that I learned. The official definition says, okay, if U consists of those components, V consists of those, this is the formula. I can't remember that. I'll put it in your formula sheet for you. You might have learned it using determinants. Okay, in which case, go wild. You might have just learned, for example, what I learned was basically to go, it's plus, 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 minus, 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 where I've kind of extended this if necessary. Whatever way you get the cross product, just make sure that you can do it. Okay. So there's a practice problem for you. So our dot product is super useful for checking if two things are perpendicular. Why do we care about the cross product? Well, for a start, the thing that I haven't said here, oh yes, I am kind of saying it over here. If you take the cross product of two vectors, the weird thing is that the thing that you get is always at right angles to both those vectors. So this is going to be super useful for us. We're going to see it as soon as we start talking about planes and things. When we want to find a vector that is perpendicular, for example, to a plane. So our cross product and our dot product, a lot of what we use them for is around orthogonality. Checking if two things are orthogonal or creating something that is orthogonal. So this bit over here is telling you that if you've got two vectors u and v that are non-zero, then if you dot it with u, so you take the cross product, dot it with u, you get that it equals 0. So this tells you that this vector is perpendicular to u. Do it again, and you can do the calculation, just write it off once to convince yourself. Dot it with v, also gets 0. So this tells us that this u cross v must be perpendicular to both u and v. And this is another of the little weirdnesses of kind of the cross product from my perspective. It takes things that were living in a plane happily together and creates something in a completely different direction. It forces you into 3 dimensions, which is kind of interesting. And sometimes it can be useful. It also gives us a way of figuring out the angle between. Cross product involves sine, dot product involves cos. So it's similar. Okay. I'm going to pause there for a moment. Any questions? Okay. So there will be some practice in the Thursday tutorial, just to make sure that you're feeling comfortable with vectors, and what we're about to do now as well. Okay, so pretty much everything we're doing in multivariate calculus is to extend the ideas from calculus. So the idea of finding rates of change, integrals, things like that. But when you did single variable calculus, you were working in 2 dimensions. You had an x and a y, and you just had lines and stuff. But as soon as you head into 3 dimensions, now we can have lines, that's great, but we can also have surfaces, we can have solids, so we need to kind of extend our ideas a little bit. So let's just think a little bit about what we're, and I will quite often go back to the 2-dimensional version that you're used to and say, okay, bring that concept over, here's how we're going to do that. So in 2 dimensions, an equation in variables in x and y usually describes a line. It doesn't have to be a function. So here's a line, but here's an equation which is not a function but describes a line. What happens in 3 dimensions? Typically, if we take an equation, it's going to represent a surface. Not always, but usually it's going to be a surface. So it'll be something like a plane, or perhaps a cylinder. X squared plus y squared is equal to 1. So notice what happens here at the top. We have, because we're in 2 dimensions, x squared plus y squared equals 1 is a circle. But when we head into 3 dimensions and we make it explicit we're in 3 dimensions, the same equation gives us a cylinder. But if you chop it on the xy plane, then you'll see your circle. So all that's happening is saying, okay, well, we need to have x squared plus y squared equals 1 is true for all values of z. And so we kind of propagate it up and down, and that's how we get our cylinder. And the same thing happens, z equals 3 is a plane in R3. Well, what's happened is if we were only in 1 dimension, we'd just have a line, but we've propagated that line. Great. So how do we talk about planes and lines in 3 dimensions? Okay, we haven't had to talk about planes in 2 dimensions because we only had one, and was the one we were working on. Well, actually, we use the same ideas as we did from 2 dimensions. So you have, for a very long time, been working with y equals mx plus c, or possibly y equals mx plus b, or whichever version you used. What is important about this? Well, we have our 2 variables, our x and our y. So our y depends on our x. Those things change. And we have this constant over here, which talks about the slope of the line. So it tells us, is it going up, is it going down, how much? So we have this idea of a slope. And then we need an additional thing, which basically tells us at least one point that the line cuts through. So we have something that is kind of giving us a direction for the line, and then we have something that is fixing where that particular slopey line goes. And we use the same idea to talk about the equation of a line in 3D. But now, if we want to talk about the direction, it's not enough to just give one number, because we're in 3 dimensions. So instead of giving one number, we can talk about direction using a vector. That's exactly what a vector is for. And in order to talk about which point our line goes through, we can't just use a single number like our C, we need to use a particular point, a 3-dimensional point. But other than that, we can put it all together and have exactly the same thing. Okay, so how do we do it? We say, well, if we've got a point P, which has a position vector x0, y0, z0, so here's our point P. So that's the point, so that is a point on the line. So our line has to go through that point. And we want it to go in the direction of vector v. So our vector v might, so I'm going to draw vector v there. But remember, we can put v wherever we like. So we put v starting there. Then, the way that so now notice what we've got. We've got a direction and we've got a point. And the only thing that we need to do is kind of get all the other points on this line. And how do we do that? Well, remember that we can scale v. So what we do is we say, okay, start at point P and add all the possible scaled versions of v going in this direction and that direction. And all the points that you get to are going to be all the points on that line. Cunning. So what does this look like? Well, it says take your point to a starting point and add to it all scaled versions of that vector. And all of these things over here will give you the points on your line. Can you? Yes? Cool. Okay. And this is called the vector parametric equation. Why is it a parametric equation? Exactly. So this brings us to the next part of a lot of what we'll talk about today, which is parameters, which don't really crop up an awful lot in single variable calculus. But here you'll notice which of these things are variables and which are constants. Here, this is a constant, and our v is a constant, and this t is a variable. So in fact, our line is just a function of one variable t, which we call a parameter, because it's not particular, it's not linked to a particular axis that we're thinking about. Okay, we will talk about these a little bit more. So this looks very much like your y equals mx plus c. And all your intuition that you have about y equals mx plus c is useful over here. It's called a vector parametric equation because it involves vectors. But if you feel like it, you can split it up into the scalar parametric equations where you basically just look at each component separately. So here's your x, and I'm going to just put this in to remind us. So if you want to just think about the x component of any point on that line, that's given by the x initial point plus the x component of the direction vector times t. Here we go. And what you'll sometimes see people do, because you'll notice here we've got 3 equations and 4 unknowns, so you can play around with those, eliminate the t, and then you get this thing, which is called the standard form of a straight line. So this, for me, when I was learning, was where things got weird, because that does not look like a straight line to me. Also, there's like 2 equal signs, and I'm not sure what the hell is going on. But sometimes it's useful. And the point to notice here is that the change in x over a is always going to be the same as the change in y over b, and the change in z over c, assuming that you're taking your x, y, and z. Okay. I have to say for myself, I still always come back to this form over here and then work from there, because that is where I still have more intuition for what's going on than the standard form, but that's just me. Quick pause, any questions? Okay. Do we want to do that? We'll come back to that if we have time. So I will put little problems in for us to do, but I think we're doing for time. This lecture ends at 1:30. Okay, I'm going to keep going. We'll come back to this if we have time. Okay, so that was lines. So spend a little bit of time, if you haven't seen this before, in kind of taking all your intuition about lines in 2D and thinking about how that translates to lines into 3D. And looking through these, because it's going to be quite important. All right, so now we come to things that we haven't really had to deal with in single variable calculus, because you couldn't really have a plane in 2D except the two-dimensional plane. But now we can have planes. They are our most basic surfaces, and we will be using them a lot. In fact, what you'll notice as we talk about, particularly in 3 dimensions, with calculus, we will start talking about tangent planes, which sort of take the role of tangent lines in single variable calculus. So in a sense, lines in our multivariate calculus lose their huge importance, and what becomes really important is being able to find planes, tangent planes, all kinds of planes. So being able to find a plane is super important. And we can use some similar ideas that we've already seen when we talked about how to construct our line in 3D. So let's think about what it is that we want to construct. We want to construct a plane. And the first thing to think about would be, well, okay, we're going to need to know one point on that plane. Just like anything else, we need to kind of position it. And then we need to find a way of talking about its direction, like which way is it sloping. And the problem with this, if you think about it in terms of lines, it would be very nice to say, well, let's just find a vector on the plane and we're good to go. But if you think about all the possible vectors on a plane, I mean, they're going in all sorts of directions. There's no one direction that we could pick that would work. But conveniently enough, and now you'll suddenly see why we care so much about orthogonality, notice that no matter where I am on this plane, the normal always points in the same direction. If I look at orthogonal to the plane, is always, well, there's 2 dimensions. It could go up or it could go down, but our orthogonal vectors from any point are always in the same direction. Aha! So that is how we construct our plane. We take our position vector, which links where exactly our plane is going to, which point our plane is going to go through, and we use the position, the normal vector, and if we have those 2 things, then we can use that to describe a plane exactly. Okay, so at this point I'm going to pause and say, think about what we learned about a line. For a line, you need to have a point, and you need to have a vector in the direction that the line goes. Okay, but if you've got a plane, you need a point, and you need the normal vector, so a vector that's orthogonal to the plane that you're interested in. Once you've got either of those situations, you're good to go. How do we do that? So we haven't quite constructed our plane yet. Well, what do we want? On our plane, we want to be able to describe all the points on that plane. What can we use? We know that our normal vector is orthogonal to that plane. So the cunning thing that we do is we say, okay, well, I'm going to create some vectors on the plane. So I'm going to take whichever point I'm interested in, and I'm going to create a vector by subtracting from it the point I know. Okay, so I'm saying I've got some position vector r, and I'm creating a vector r minus r naught, because that definitely lies on the plane. Okay? And now, because it lies on the plane, I know that it has to be perpendicular to my normal vector. So I dot my vector that I just created with my normal, and it has to be equal to 0. And any vectors here, or any position vectors here, which make this true, must lie on the plane. Cunning. Pausing for a moment. Make sense? Yeah? Okay, so again, just to make it absolutely clear, this bunny over here is a constant. This bunny over here is a constant. So we create a new vector which definitely lies parallel to the plane. So, I mean, vectors can lie everywhere, but it lies parallel to the plane. And we dot it with our normal, which is perpendicular to anything in the plane, and they must be equal to 0. And therefore, by solving this equation, I can find all those possible points. And this is called, very unimaginatively, the point normal equation of the plane. So my recommendation is that you get this as deeply embedded in your psyche as y equals mx plus c. Which, I mean, if someone had told you the first time you saw y equals mx plus c that you were going to get it so muscle memory embedded, you would have been like, I don't think so. But it happened. How did it happen? It happened by doing lots and lots of examples, practicing. Okay, so we're going to practice finding equations of planes as many times as you did y equals mx plus c, and we'll be there by the end of this course. So you can turn this, so remember, let's just look at what this looks like. So we've got a bunch of vectors sitting in there. We've got our n and our r and our r0. But ultimately, this is a scalar equation because there's a dot product. So whatever happens over here, we need to get out one number, and that number needs to be equal to 0. So another way of looking at this equation is to split it up and imagine each of these components and then multiply out, do your dot product. And if you do that, so here, what have I done? So I've got a normal, which is A, B, and C. And then I've got my R, which is X, Y, and Z. And my R0, which is X0, Y0, Z0. And when you do the dot product, this is what you end up with. And if you multiply this out, then you'll get an A times X and an A times X0 with a minus sign. And that, remember, A times X0, that's just a number. B times Y0 is just a number. C times Z0 is just a number. So another way to kind of sort this out is to just group all those constants, pull them over, and then you end up with this form over here, which might look more familiar for those of you who've worked with planes before. The glorious thing about this, if you get handed a plane in this form, for example, 2x plus 3y minus z is equal to 1, is that you can look at it and immediately tell me the normal. Because based on what we've done over here, the coefficients of x, y, and z just give you the coordinates of the normal. So this plane has a normal 2, 3, minus 1. So it's a pretty useful form. Yeah?
Is that true even if v is like 4?
Yeah. I mean, then it's just a different, it's a vector that's in a different, so it has the same, so if we had the plane 2, 3, I mean 2x plus 3y minus 1z equals 4, how are they related? How are the two planes related? They're parallel. So this number over here is kind of encapsulating these terms here, a times x0, b times y0, c times z0, which encodes the information about the point that the plane goes through. But the coefficients of your x, y, and z encode the information about the normal. So it's a very nice form. I hand you a plane, I say what's the normal, you say blah blah blah. We're done. Okay. But it also makes it quite quick if I hand you a normal and I say find me the plane that has this normal and goes through this point. It's also quick, and you have a check to see if you get it right when you get this. Okay. Pausing. More questions? All right, so here you go. Here's a question to do. Find the equation of a plane, an equation of a plane that passes through the 3 points given by those points there. So I'm going to see if there's useful stuff that I can... You're welcome to talk amongst yourselves. So this is going to pull together pretty much everything we've done in the lecture up till now. Yes? Oh, Brooke. So a good place to start is to think about what ingredients you need to bake a plane. What are the two things that you need in order to have a plane? You need a normal and a point. Okay. You've got a lot of points there, but you ain't got no normal. Build one.
You can
Ah, yes. See, cross product.
So basically you just pick up 2 points and you can also
So you need to construct 2 vectors on a plane.
yes, and then you make it and then you make it.
Quick question, do you want us to give the answer in terms of the point normal equation or in
coordinates or something.
Whatever floats your boat. I mean, so my recommendation would be to always multiply this out, because then you can check that your normal is the right normal. But yeah. Okay, so if we think through this problem, and this is going to be a thought process that you're going to need often, because you will often be asked to find a plane that does blah, or a plane going through wherever. And the thought process that you need to have goes, okay, I need to bake a plane. That means I need a normal and I need a point. And just as often when you were finding the equation for a line, sometimes you were given the slope, sometimes you were given just 2 points on the line, and you had to construct whatever you needed to find a line. The same thing goes with finding the equation for a plane. You need to construct the stuff you don't have. Okay, so we need to have a point on the plane, and we need a normal. Well, we have way too many points. You can pick any one of those, and that will do. But the thing that we don't have is a normal. Okay, so that's what we need to construct. So if we think about it, we've got some plane that we're interested in, and it has those 3 points on it, wherever they are. And what we want is, at one of those, well, at some point, we need to have something that is perpendicular to our plane. And because our lecturer spent a lot of time in the first half hour ranting on about orthogonal things, we think, well, could I use a dot product or a cross product somehow? And then if you go back, you'll remember that I said, well, the dot product is super useful for finding out if two things are orthogonal. The cross product is super useful for constructing things that are orthogonal. Ha, okay, so maybe we could use the cross product. What do we need in order to use the cross product? Well, we need to have two vectors that we want the third to be orthogonal to. Can we find two vectors? Well, we have some points, so all we need to do to find some vectors that are lying on the plane is, for example, to have a vector from there to there, or maybe a vector from there to there. So pick any of those points and construct for yourself two vectors by saying, for example, p minus q, or q minus p. It really doesn't matter. And that will give you a vector. So in our quest for the normal, we need two vectors to cross product. Okay, so let's construct two vectors on the plane. I'm going to call vector 1 A. Should we take p minus q? I don't know. Is there one that's easier? Yes, p minus q is good. Alright, so I'm going to say point p minus point q. I'm treating those as vectors, is going to be 1 minus 1 minus 1. But you could have gone q minus p, you could have gone p minus r, so there are 6 possible vectors that you could construct here. Who should we take for b?
R minus B, maybe.
Okay, let's take r minus
P.
p. Okay. So that's 2, 1, I think. Did I do that right? Okay, so that gives us two vectors that lie on the plane. Now we cross product them, and our normal is going to be A cross B, and it could equally well be B cross A, because then we would get the vector that is in the same line as A cross B, but pointing in the opposite direction. It doesn't matter, we don't care, we just want something that's orthogonal. Take A cross B, and that will give us our normal, and that's more algebra than I'm prepared to do. But if you do this and get it correct, then you will get an n, and you just plug it in there. And you're good to go. Yes? Questions? Yes.
There's potentially a faster way to do it.
Okay.
If I'm allowed to
Go for it.
elaborate. We know that the equation for the plane, if we wrote it as in terms of x, y, and z, it would be ax plus by plus cz equals
Yep.
some d.
Yep.
We have 3 points. We can just substitute the points in for your x, y, and z.
Yep.
Because the d stays constant, you can equate your equations.
Yep.
You have 3 linear equations and 3 variables.
Yep.
You can solve them.
Right.
You will, however, get something times one variable c. The c can be completely ignored because there are an infinite number of normals to any given plane.
Yep.
They just vary in distance.
Okay, so as was pointed out, there is another way of doing it. I would debate whether it's quicker, but you can just form yourself, you know the form ax plus bx plus cy,
Ax plus
Whichever,
by plus
this
cz equals.
this form, you know that it needs to form this form, plug in your x, y, and z for each of your 3 points, solve for a, b, c, and d. That's a quick way. If you're good at solving systems of linear equations quickly, which I'm not. However, I would say, please make sure that you are comfortable with this way, because this way is going to work much more generally, depending on the number of points and things that you have. So you won't always just be given 3 points. Okay, more questions? Yes?
Can you show exactly how we add our normal into the equation you showed?
Sure. Okay, so our normal is going to come out as, you're going to make me do a cross product in front of the class. Okay, fine, once. I will do this for you once. Unless someone else can do it quicker. Okay, so that's going to be 1
G minus J, J hat minus J.
j hat?
If I did correctly.
Okay,
J hat
The
minus
last
You have K, you have two
wrote
J's instead of a
IJJ
K.
in the first lines. It should be IJK.
okay,
J hat minus J hat.
okay. So thank you for your support. We're,
If it's correct.
okay. So if you do that cross product and it's correct, I think this looks right, so that's going to be, that's a 1 plus 1, wait, 1, I'm not sure. Okay. Alright, I'm not going to do this too quickly, I'm going to, okay, so that's I hat minus 1, so that's plus I hat, that's minus j hat, minus plus j hat, it's a k hat,
It should be minus 2 j hat plus j hat.
so sorry, minus j hat plus,
Minus 2 j hat plus j hat.
okay, so then we do have, okay, yes? Yes, okay, take your working. I think you forgot to minus something.
I got the same, but just like with the whole thing minus, with like other.
Okay. Okay, so here's our normal that we just worked out, probably. We seem to be getting to a consensus. Now, depending on which vectors A and B you picked, your normal might look different. Okay, so you might have a normal in the completely opposite direction, and you might have a multiple of this. But your normal will be some multiple of this thing, because all the normals are parallel. Okay, so this is the slightly weird thing. You can have equations for a plane that are the same plane, but that look different. Okay, so assuming that this is our normal, what do? Well, we need to have, so we know that our equation is n dotted with r minus r naught is equal to 0. We've got our normal. I'm going to change form here. I'm dotting it with, And now we need our r minus r naught. And remember, our r naught is any point on the plane. And we have 3 to pick from. Which would you like?
P.
P. Okay. All right. So then we've got to have x. So we're going to take P, which is 1, 1, 0. And remember, our r is x, y, and z. Those are actual variables. So we say x minus 1, y minus 1, z minus 0, and that has to be equal to 0. Question? Okay, so notice again, there's another place where things might be different, because you might have put in a different point here. So if you'd put in Q or R, then you'd have different things happening over here. But that's okay. Alright, so here's our point normal form, but let's just multiply it out and check that things work. So we've got 2x minus 2 minus y plus 1 plus 3z minus 0 is equal to 0. So we've got a 2x minus y plus 3z is equal to 1, I think. Yep. Okay. And now, because we are paranoid bunnies, we check, are the coefficients here the same as my normal? Or did I screw up somewhere along the line? 2 minus 1, 3, 2 minus 1, 3. Huzzah! Okay. And if you were even more paranoid, and if we had more time, the next thing that we do is we plug one of those points in and check that this side equals 1. So in fact, let's just do that. All right, so if we plug in 1, 1, 0, we get 2 minus 1, which is 1. And that's great, because that's 1. Okay. Yay, so we're probably good. Yeah? Okay, did that help? Yeah. Okay. Yeah.
Is there a way to, when you get the normal vector, to directly put it in the ax plus by and c equals 1?
Sure. So the question is, can you, once you've got your normal vector, did we have to go through this dot product stuff? No, because you could have said, well, I know it has to be ax plus by plus cz equals d. You know that this is going to be 2 minus 1 z, so plug those in. Then pick one of your points that you know has to lie on the line, like 1, 1, 0, and work out d. Yep. Okay. Please get comfortable finding equations for planes in all shapes and forms. I will help you as best I can by giving you lots of tutorial problems, lots of problems in the online quizzes, but it's up to you. This needs to get as comfortable as solving y equals mx plus c, because we're just going to use it all over the place. Yeah. All right, so that is your mission. All right. So I want to mention this, but it is not super important at the moment. So you spent a lot of time when you were learning calculus, you learned about quadratic equations, parabolae, things like polynomials, things like that. And it's obvious as soon as you head to more dimensions, we just kind of keep doing the same thing. And we come to the idea of talking about quadric surfaces. So these are linked to, in 2 dimensions, you would have a quadratic, which is ax squared plus bx plus c equals something. That's your equals 0. That's your quadratic. Here we've got quadric surfaces. And the most general equation should look quite similar. So again, we've got squared terms, x squareds and y squareds. But now we've got mixed partials. So we've got x, y. And that d is not a differential. That's just a constant. And f and so on. And depending, so just like when you're studying in 2 dimensions, depending on what you have as your coefficients in your ax squared plus bx plus c, depends on whether you get circles or I mean, depends on whether you get parabole or hyperbole or that sort of thing. Depending on your coefficients, you get parabolas, you get hyperbola, hyperbolic plates, things like that. You get spheres, you get ellipses. And that gives us our quadric surfaces. They get a little more tricky than dealing with the two-dimensional versions, and we're not going to spend a lot of time. But one of the things that you can do is, for example, so I'm just going to show you, you can get cylinders. So those are kind of exactly like you would so that we've seen this before, x squared plus y squared equals a squared, gives you a circle in 2 dimensions, a cylinder in 3. If you want to get a sphere, then you need your x squared plus y squared plus z squared equals a squared, which is centered at 0. If you want it centered somewhere else, it looks like this, but this should look very similar to your equation for a circle. So a lot of your intuition will work. And then we have parabolic cylinders, where basically we've taken a parabola and we've just extended it in various directions. And you can spend some time having a look at these graphs of kind of common quadric surfaces. So we have an ellipsoid, an elliptic paraboloid, hyperbolic paraboloid, cones, and various things. And all of the names, if you cut along one of the coordinate planes, you will see the shape of the two-dimensional thing that you're used to seeing. So they're just extensions. And we will play around with some of them, but there's not a lot that needs to happen here. So for homework, go and see if you can figure out, if I hand you one of those equations, what is that bunny? I would highly recommend that you get GeoGebra or some other graph plotting program that makes you happy. GeoGebra is free, it's online, it's pretty good, and you can just type in the equation and it draws it for you. It's delightful. Okay. Pausing here for a moment. Okay. So, you might have in your head, depending on whether or not you've taken a class with me or not, some version of a function where it's kind of like, well, you put a thing in and you get a thing out. The formal definition, well, a formal definition of a function is a rule that assigns to each element in a set D, which we're thinking of as a domain, and a unique element called f of x in the range. So the key thing about functions is that we have an input and an output set, and we have a rule that takes things from input to output, but you can only ever take an input to one output. So this is totally fine, but whoops, that is forbidden. So I can't take this input to 2 different outputs. Okay, function. And you have dealt with many, many functions in your lives. Most of maths that you've been dealing with has been functions. And now, because we've got vectors, we have a whole new way of constructing functions, because having vectors means that we can use vectors as inputs. And similarly, we can get vectors as outputs. So long as we obey the function rule, there's no reason to say that we can't have a vector input and get a vector output. And in fact, most of multivariate calculus is going to be about understanding how these crazy new functions work. So we're going to look at functions which take as an input a scalar, but spit out a vector. We're going to look at functions which take in a vector and spit out a scalar. And we're going to look at functions that take in a vector and spit out a vector. And we want to do the calculus of all of those. So far, the calculus that you've done has been the calculus of functions that take in a scalar and spit out a scalar. We're expanding that idea because it turns out to be useful. So where are we starting with? We're starting with the idea of a function which takes in a scalar and spits out a vector, which initially might seem strange, but the picture to have in your head is we're imagining that we have, I don't know, a fly that's buzzing around, and over time, so for each value of time, we want to plot its position. So essentially we want to put in a time, a scalar, and get out a vector, its position. And more generally, this gives us the idea of what are called parametric curves, or curves in 3 space where, depending on the time, you can tell me what the position is.
So I'm picking a scalar that is not dependent on the axis.
Right.
Okay.
Yeah. And in fact, there are often many scalars that you could use that would give you the same curve, and we'll see a lot of that. Yeah. So it's just some number, and it's useful to kind of have time because we're kind of intuitive there, but it doesn't have to be time. Some number which goes along its own particular axis, and depending on where you are on that axis of that little independent thing that's doing its own thing, depending where you are, you put that number in and you get out an x and a y and a z. So if we think about this in terms of kind of things that we can get a handle on, our position of our fly that we're monitoring at any time is given by r, which has coordinates x, y, and z. And x and y and z are each changing with time, with our parameter. So they are each a function of time. Okay? So just to kind of put this all in kind of the notation that we've been using so far, we know that x is a function of time, y and z as well. So when we think of our position as a function of time, we're thinking of it as a vector where each coefficient varies over time. Yep. I'm not saying anything very profound. I just want to make sure that you have the different notations because we'll use all of them. Okay, so as our parameter increases, then we can think of our particle as moving along a path which creates a curve in 3 space. Okay, so we've got some way of measuring the position of a particle, and this is where I'm kind of pulling on the physics intuition here. And probably immediately, I'm sure if you've done any physics, you'll be starting to think, okay, well, if we know about position and changes, we want to talk about velocity. Okay. Yay! And as soon as we want to talk about velocity, we need differentiation. Woohoo! Calculus in 3 dimensions. Here we go. Okay, so this is really what we're trying to do. Okay, we have a curve, we have something moving in 3 space, described by a vector, and we need some way of talking about its velocity and its acceleration. And that means we need calculus, but we need it in 3 dimensions. But we can use the ideas that we have from calculus. And so if you think about what you did in calculus, if you wanted to measure the rate of change, and some better color, so in 2 dimensions you wanted to work out the rate of change of something from there to there, you looked at this line here, and you looked at the slope, you looked at dy by dt, and then you actually you did it with deltas, delta y by delta x, and then you took the limit as delta x went to 0 of that thing, and you got the derivative. And then you spent a lot of time working on limits and calculating derivatives, and it was all fun. Yes. We use the same idea here. Okay, so here's our curve, and our little particle is moving from here to here. What can we say? Well, we can start as we did in 2 dimensions with the idea of an average velocity, so the change in position over time. So we could say, okay, well, it's going to be the position where it ends up minus the position where it started, divided by delta t. And then we play the game of making delta t really, really small. So we let delta t go to 0, and everything we learned about limits and derivatives in calculus 1 is useful here. If we let the limit as t goes to 0 of this bunny over here, we get the derivative of r of t, which is our velocity. And it looks weird because we've got a vector in there that we're taking derivative of, but remember that vector has scalar components. So what we really have, what we say here is our v is equal to dx by dt, dy by dt, dz by dt. That's really what we're saying. So when you have to find the velocity in 3 dimensions, and you have each component, and you have how those are changing by time, your velocity is just the derivative of each component individually. I just swept a whole lot of maths under the rug. I would love to have kind of gone through in detail, but trust me, it works. So long as the usual provisos, you have nice smooth curves, nothing hinky, the usual calculus 1 provisos. Okay. So that's just what I basically said over here. So this is a little expansion of what I wrote, but there we go. Okay, so things to note. Our velocity vector is tangent to our curve at r of t. So this is exactly what you know from calculus 1. You know that when you find the tangent curve, the tangent to a curve, it's always a tangent in 2 dimensions. The same thing happens here. So our velocity vector is always tangent. You can find your speed by just finding the magnitude, as you might expect. And with joy and delight, if you want the acceleration, you just do the same thing again to the velocity, and we're good to go. Yep. Okay, so I think I just did that. No, I didn't. Okay, so to show how straightforward this is, here we've got a particle that's doing some weird thing. Okay, but the point is that it's moving with respect to time in x, y, and z, and we want to find the velocity and the acceleration. What do? Well, we just dive right in and we differentiate. So we differentiate term by term. Derivative of cos of 3 cos omega t
is minus 3
with respect to t.
is
Yes?
minus 3 omega sine. Should be minus.
Okay. Derivative of 4 cos omega t. And derivative of 5 sine omega t.
5
Plus
5 omega.
5 omega cos omega t. Okay. Do it again to get your acceleration. Okay? If this is feeling hazy, just remind yourselves about derivatives of trig functions and also chain rule. If you were wondering where these omegas came from, go and revise your chain rule. Okay, so it's dead simple. It's just now you have 3 derivatives to take instead of 1. Sorry about that. At least we're not in 10 dimensions. And we can talk about differentiation rules. You're welcome to look through these. They're kind of what you would hope. So if I'm adding 2 vectors together and taking the derivative, it's the same. So that looks like the familiar addition rule for derivatives. Same for constants. And you have the product rule if you have some function, notice not a vector function. Okay? Because in a scalar function, times by u, so this is the same as our constant times u, then you have a kind of similar product rule thing going on over here. The things that get slightly different are where you need something for our dot and our cross products. Dot product looks exactly like the product rule, so that's nice. And in fact, our cross product does too, so yay. Okay, great. And finally, here's our chain rule. Okay, so I'm not going to spend a lot of time. Look through these, get comfortable with these. Whew. Okay. So the final thing that we need to talk about today is parameterization a little more generally, and you'll get quite a lot of this in the tutorial. So we happened to be using the parameter t and thinking of it as time, but we don't really have to. So we could, for example, instead just pick some arbitrary scaled thing and use that instead of time. And there will be situations where For example, you might want to use an angle as a thing that you parameterize by. So we need to talk a little bit more about parameterization. Okay, so let's just clear up what it is. It's expressing the state of a system, process, or model as a function of independent quantities, which we call parameters. So this comes back to the idea that the thing that we are describing our system in terms of is not one of the axes we're working on. So if we're talking about position, which has x, y, and z, where our position is dependent on something else, perhaps time, perhaps some other abstract thing that has its own scale that it works on. So, I mean, for me, I find quite useful sometimes to kind of have in my head the picture that here is the curve that I'm describing, my C of t, and over here I have the axis that is describing t. It's doing its own thing over here. It's unrelated to what's happening here. So let's take a simple example. So it's going to turn out to be pretty useful to be able to parameterize things. So we've got the plane x plus y equals 1, and that intersects the paraboloid z is equal to x squared plus y squared in a parabola. Okay, and we want to parameterize this parabola using t equals x as a parameter. What now? Okay.
So that would be my idea. You write t in place of x, and then you just have a linear system with two equations because t is considered as the known.
Right.
And then you solve it.
Right. So let's be I mean that is essentially what you're doing. But let's think about what we want. Okay. So I'm going to use GeoGebra just to show you. So we've got okay, so we've got x plus y equals 1. Alright, and what was our squared plus y z? Okay, and what I probably need to do and what I actually, okay, so the mistake that I've made at this point is I didn't make this as a plane. Okay, so here's my paraboloid, and so this at the moment is shown as a line, but I actually want a plane x plus y equals 1, which is a plane that cuts like that. And if you think about how it cuts, I wonder if I do this, let me just delete this. Better. All right, so here you can start to see what's happening. I've got my paraboloid, I've got my plane, and if I look like this, you can see that where that plane cuts the paraboloid, I'm getting a parabola. So that's kind of nice, but now what I'd like is to have some equation which tells me if I put in a parameter where I want an equation for that intersection. I don't want to have to keep saying, well, take the paraboloid, take the plane, and cut it. And one way to do that is parameterization. So what I want is something that ends up with being an r of t equal to x of t, y of t, z of t, which as I let t go from minus infinity to infinity will map out that parabola that I'm interested in. Okay, so I'm hunting for these three equations over here. Well, let's see what we can do. So the first thing is I told you to parameterize it using t is equal to x. So that solves our problem for x of t. So we've got x of t is equal to t. Okay. What else can we do?
X square is equal to t square. I mean, x square.
Right, so we've got these two equations, and we know that they both have to be true.
Yeah.
So let's plug in. So I mean, I would actually recommend you use this one.
Yeah, it's first one. Yeah.
Yeah. So then we've got, well, t plus y is equal to 1, so y is equal to 1 minus t. So that has to be true. And then finally, so that gives us y of t is equal to 1 minus t. And then finally, to get our third point over there, let's use this equation over here. So our z of t is going to be equal to t squared plus 1 minus t squared. And you could simplify that up. And so what we end up with is that r of t is equal to t 1 minus t. Let's just multiply this out. That's a t squared plus 1 minus 2t plus t squared. So that's 2t squared minus 2t plus 1. And now we have a parameterization. So this doesn't necessarily look like a parabola that you would expect. But if you let t vary from minus infinity to infinity, it will map out that parabola for you. Make sense? Okay. So, give me 1 minute, please. 1 minute, and you will. So, things to note. Parameterizations are not unique. So one thing to have a look is to convince yourself that these three quite different looking parameterizations actually represent the same curve. There's some notation, some vocab that you can learn there. Here's something to practice. And we will finish up arc length, I think, at the start of next lecture. But what I would like you to do is just have a look through these notes so that we can be fairly steady. So the idea here is just we want some way, if we have a curve described parametrically, we'd like to be able to measure the length of bits of that curve. How do we do that? All right. Well done, everybody. So your first tutorial is parameterization, which I think will be helpful.